Hello and welcome back to the series. Thank you for joining me for another Unity UI Toolkit video. In this video, we are going to focus entirely on event-driven programming. We already touched event-driven behavior earlier when we created the custom toggle button. This time, however, we're going to use the same general idea at a broader architectural level. Instead of allowing ShipUI to directly manage all drive-related values and update every visual element from multiple places, we're going to introduce a separate ShipDriveModel. That model will store the current impulse speed, warp factor, active drive, energy consumption, and total available energy. Whenever one of those values changes, the model will raise a C# event. ShipUI will subscribe to those events and react by updating interface, audio, parallax speed, button style, and progress bars. Let us start with a problem we are trying to solve. Until now, we've placed all behavior directly inside UI callbacks, and this works. But another control also changes impulse speed. The activate button sets the speed to 6. The deactivate button sets it to 0. Later, perhaps an autopilot system, gameplay logic, networking code, or a save game also changes the speed. If every place that changes impulse speed must also know how to update the label, tracker, energy bar, parallax background, button style, and audio pitch, then the same logic quickly becomes duplicated. This creates several problems. One code path might forget to update one of the UI elements. Another code path might use a slightly different calculation. Gameplay logic becomes tightly coupled to the interface. And as the project grows, it becomes harder to understand which part of the program owns the actual state. The event-driven approach solves this by creating a clear flow. Instead of every color updating the complete interface, the color changes only the model. The model validates and stores the value. Then it raises an event. The UI listens to that event and updates everything that depends on the new speed. This gives us one source of truth and one consistent reaction path. Event-driven programming means that parts of the program reacts to events instead of constantly checking every possible condition or directly calling every dependent system. An event represents the fact that something happened. UI Toolkit already uses this pattern extensively. A button dispatches a click event. A slider dispatches a change event float. Or a custom toggle dispatches a change event bool. In this video, we add another event layer. The UI control event writes into the model, and then the model raises an ordinary C# event. This is useful because the model does not need to know anything about UI Toolkit. It does not know what a slider, label, progress bar, or USS class is. It only owns drive-related state and calculations. The model is called ShipDriveModel. It specifically manages the drive system, impulse speed, warp factor, active drive, drive energy consumption, and remaining energy. The model is plain C# class. It is not a model behavior. It is not scriptable object, and it does not use any UI Toolkit type. That makes the model lightweight and independent. It could be tested separately, used with another UI, or even used without UI. Before the class, we define an enum, drive mode. An enum represents a small set of named values. In this case, the ship can have one of two active drive modes, impulse or warp. This is better than representing the active drive with a boolean such as is warp, because the enum clearly expresses what a value means. It also leaves room for additional modes in the future. The important architectural change is that the model now knows which drive is active. Now the model owns this information directly through active drive. The model defines maximum values, max impulse speed and max warp factor. These define the valid ranges for the two controls. It also defines the initial states, default impulse speed and default warp factor. The ship begins at impulse speed 6. The warp slider begins at factor 1, but warp is not active. These defaults match the values altered in the UXML. However, the important point is that a model owns them. The UI should display the current model state. The model should not depend on whichever default value happens to appear in the newly created visual tree. The energy limits are max impulse consumption and max warp consumption. At the maximum impulse speed, the drive consumes 30%. At the maximum warp factor, warp can consume 100%. The model stores its current state in private fields. Private fields cannot be changed directly from outside the class. That is important because we do not want another script to silently assign a new speed without validation or without raising an event. All changes must go through public methods such as setImpulseSpeed, setWarpFactor, setActiveDrive. This lets the model control the complete change process. When the model is created, it immediately calculates a consistent initial energy state. The active drive is impulse, and impulse speed starts at 6. So the constructor calculates impulse consumption and the corresponding total energy. At this point, there are no subscribers yet. That means the events are still null and nothing is notified. That is fine because later, when the UI subscribers, it will perform an explicit synchronization using the model's current values. The model declares 4 events. Action float is a built-in delegate type. It represents a method that accepts one float and returns nothing. The event keyword controls ownership. Other objects can subscribe and unsubscribe, but only ShipDriveModel can raise the event. This protects the meaning of the event. Only the object that owns impulse speed is allowed to announce that impulse speed change. The model exposes its values through read-only properties. These are expression-bodied getters. Outside code can read a value, but it cannot assign to it. The calculated consumption properties are impulse consumption and warp consumption. These values are not stored in separate fields. They are calculated whenever they are requested. The active drive is changed through setActiveDrive. If the requested drive is already active, there is nothing to do. If the mode changed, the model stores the new active drive and recalculates energy consumption. Switching from impulse to warp does not change either slider value. It only changes which drive is currently consuming energy. This is why energy must be recalculated even though meter speed property changed. The warp toggle in ShipUI calls setActiveDrive. If the toggle is on, the model receives drive mode.warp. Otherwise, it receives drive mode.impulse. From this point onward, the model itself knows which drive is active. The impulse slider is set impulse speed. First, the value is clamped. Even though the slider has its own limits, the model should validate its own data. The slider may not always be the only color. Next, the model checks whenever the value really changed. Then the model stores the new value. After that, it raises impulse speed changed. The null conditional operator checks whether at least one listener exists. Finally, the model recalculates energy only if impulse is currently active. The same logic is used in setWarpFactor, but energy is recalculated only when warp is active. Now let us move to ShipUI. The class has field ShipDriveModel, DriveModel. The model is created once in awake. This is an important change. The model represents the gameplay state. Its lifetime should match the game object's lifetime, not the visual tree's lifetime. The UI tree might be rebuilt. By creating the model in awake, it survives UI reloads. The UI initialization is divided into smaller methods. Here, the important point is that every method has a clear responsibility. Query elements finds controls and visual elements. Configure initial control state enables impulse controls and disables warp controls. Register UI callbacks handles UI Toolkit input events. Bind drive model connects model events to UI reactions. Breaking the setup into named methods makes the code easier to read and explain. Here, each plus equal subscribes a UI method to one event. The opposite operation is grouped in unbind drive model using -equal. Unsubscribing matters. If the UI reloads and we subscribe again without removing the old subscriptions, the same handler will be added multiple times. One model change could then update the visual element several times. The old subscriptions could also refer to elements from a visual tree that no longer exists. That's why the code unbinds before reconnecting to a new visual tree. It also unbinds when the component is disabled. A good general rule is whenever you subscribe, decide where you will unsubscribe. Using minus equal for a method that was not previously subscribed is safe. It simply has no effect. After subscribing, bind drive model calls synchronize drive UI. This is one of the most important parts of the implementation. Subscribing to an event only means call this method when a future change happens. It does not automatically send the current value. Without synchronization, the freshly created UI could display default values stored in the UXML until the user touches a control. Even worse, if the model already contains a different runtime state, the UI would be out of the sync. The model is the source of truth. So synchronization reads values from the model and applies them to the UI. The impulse event handler updates everything that depends on the impulse speed. This method reacts to the model. It does not write back into the model. The model announces the new speed, and the view reacts. The warp handler always updates the tracker and numeric label. However, warp should affect ship speed and audio only when warp is active. The energy handlers update the consumption and total energy progress bars. The model stores normalized values from 0 to 1. The progress bars use values from 0 to 100. So the handlers multiply by 100 and format the title as a whole percentage. The progress bars never write anything back into the model. The slider callbacks are intentionally small. The UI callback forwards the new value to the model. It does not update labels, trackers, progress bars, audio, or parallax directly. Those updates happen after the model accepts the new value and raises its events. The activate and deactivate buttons also modify the slider, which follows the same path. This implementation uses explicit C# events. Unity UI Toolkit also provides a built-in data binding system. The two approaches solve related problems, but they have different strengths. UI Toolkit data binding can reduce repeated synchronization code. However, data binding does not eliminate events and callbacks. Button clicks, animation triggers, sound, scheduled transitions, and other commands still need behavioral code. In the next video, we will introduce UI Toolkit data binding on other parts of the same spaceship interface. The goal is not to immediately replace the drive system. Instead, the project can demonstrate a hybrid architecture. That is everything for this part. Thank you for watching. If you found this video useful, please consider liking and subscribing on the channel. Feel free to leave questions or suggestions in the comments, especially if there is a specific UI Toolkit topic you would like to see in the future video. In the next videos, we will continue building the spaceship interface and introduce more advanced UI Toolkit workflows. See you then.